time. We can't touch it, we can't see it, yet every one of us is aware of its passing. Our perception of time shapes our view of the world. But what if we could widen that view by manipulating time? What does the world look like if time speeds up? What would we see if time slowed down? Now we can do just this and see our familiar lives in startling new ways. To see such different time worlds is a magical experience. But we don't need magic to manipulate time like this. Modern technology, ultra-high-speed cameras and sophisticated time-lapse photography, combined with powerful supercomputers, all reveal aspects of our world, our universe, that defy belief. We're about to enter a strange world, a place beyond our normal perception. A place where we can see events normally hidden from us. Some, because they're so slow they never seem to change. And some, so fast they're over in the blink of an eye. Throughout the ages, people have been obsessed with measuring time. The path of the sun or moon across the heavens is nature's clock. And the sun provided humanity with our first clocks. Our ancestors noticed that the sun follows a predictable path across the sky, so time could be tracked by the position of the shadows it cast. Very accurate, as long as the sun shines. Mechanical devices that track time even more accurately and independently of the sun or moon were vital in expanding our knowledge of the world. But these instruments also gave us a sense of time passing in a regular way, like clockwork, that it had its own fixed reality. We're so confident of the regular beat of time that we organize our modern lives by the ticking of clocks. But time is an elusive concept, and almost certainly doesn't exist in the way we think it does. After all, Albert Einstein showed 100 years ago that time is relative. An experience understood by every football fan. Their perception of time changes depending on the course of the game. The elation of scoring a goal soon fades. Defending a slender 1-0 lead makes time pass very slowly. For this half of the stadium, the end of the game and victory seems an eternity away. For fans of the losing side, the end of the game is approaching far too fast. Time seems to have sped up. Surely there can't be enough time left for an equalizer. And then time slows down again. The experience of a sublime moment seems to last forever. Yet, however variable our experience of time seems to be, we do have an accurate timer ticking away inside our heads. Scientists call this effect interval timing. It coordinates everything from speech to walking, yet is one of the least understood functions of our brains. Tap a beat without being aware of it, perhaps out of boredom, and you'll fall into the same rhythm that everyone else does. About one beat every half second, suggesting that we have our own built-in metronome somewhere in the brain. Yet there isn't one distinct part of the brain that ticks away, measuring time. The whole brain is awash with different rhythms, like an orchestra, all being monitored by one particular part of the brain, the striatum, acting like the conductor, extracting an underlying rhythm that gives us our interval timing. But that basic rhythm can be modified. The human brain is very good at recognizing the slightest change in rhythm, and it's synchronizing to external patterns. A flamenco guitarist and dancer improvise a lot during their performance, but they stay in sync even through complex rhythmic changes. Our internal beat is crucial to the perception of time. Our senses only sample the world at intervals, otherwise we'd be overwhelmed by information. And the rate of sampling seems to be driven by that internal beat. This sequential sampling creates our perception of time, of a series of events happening one after the other. But our internal rhythm changes with age. A child's metronome runs faster than an adult's, though only by a few tenths of a second. Is this why we feel that time seems to go faster as we get older? Since our perception of time can change, and our internal metronomes are so adaptable, can we teach our brains to extend the limits of our everyday time perceptions? Martial arts experts do just that. Their brains can slow down time so they see and react to lightning-fast moves that leave untrained watchers amazed. This also happens in other sports, when someone is said to be in the zone. It's like stepping outside the normal flow of time. But there's another way to change the perception of time, which seems to be the complete opposite of martial arts. We measure the passage of time subconsciously by occasional references to our interval timers. so we can stretch time by focusing attention away from our internal clocks. This is what a Buddhist monk does when meditating. In being attentive just to the present moment, time seems to slow down. When the Dalai Lama described his experiences of meditation to a group of neuroscientists, they realized that meditation changes time in the same way as being in the zone. As a monk rouses from meditation, more time seems to have passed than really has. If individual humans can experience altered perceptions of time, it's no surprise that other animals may be able to perceive time in very different ways. A sense of the speed of events passing partly depends on the raw information received by the brain. Show a human a series of images one after the other, and they fuse into a continuous stream when the rate is greater than about 60 a second. For a fly, the images don't fuse until they reach nearly 300 per second. So flies get more information from an event than we could, which is the equivalent of seeing things much slower than we do. And flies need to. Fast flight in confined spaces needs lightning reactions. This gives flies their extraordinary aerobatic skills. And makes them very hard to swat. Flies are much better at seeing and reacting to fast-moving events than we are, but our ingenuity allows us to extend our perception of time far beyond our biological limits. With modern technology, we can slow down and analyze events in the natural world that are so fast they're over in an instant. And this reveals some big surprises. The mantis shrimp feeds on hard-shelled creatures like crabs and clams. It uses its claws to hammer the shell, and can even break the toughest shells with a strike so fast it's impossible to see at normal speed. We have to expand time to understand why the shrimp is so deadly. At this speed, the blink of an eye would last 20 seconds. Scientists have measured the claw's speed at 23 meters per second, the fastest strike in the animal kingdom. To accelerate to this speed, the claw experiences an incredible 8,000 G and hits the snail with a force equivalent to more than 100 times the shrimp's body mass. Yet the shell isn't broken by the force of this impact. It's shattered by air bubbles. At the moment of impact, a bubble forms next to the shell, which cavitates, collapses, with enough energy to produce a loud sound and sometimes even a flash of light. The huge negative pressure created by this collapse smashes the strongest shells. By slowing down time like this, we can appreciate the natural world in exciting new ways. Arowana are large predatory fish from tropical rivers. They patrol just below the surface, looking for insects, frogs, or lizards on the overhead branches. And when they see one, a big arowana can jump 2 meters with deadly accuracy. But the prize for the most accurate fish goes to the archer fish, which also takes prey from above the surface. It can jump, but it has a much more efficient way of feeding. It can spit with deadly accuracy and hit an insect nearly 2 meters away with enough force to knock it off its perch. The action had to be slowed down over 100 times before scientists could work out how the archerfish does this. First, it positions itself directly under its prey to reduce distortion through the water's surface. Then it takes aim. An archerfish can't move its lips, so it aims by lining up its whole body. Its tongue is shaped to form a groove against the roof of its mouth like a rifle barrel, and a powerful contraction of its gill muscles fires the shot. An anglerfish uses the opposite technique. Suddenly expanding its mouth creates a powerful suction, enough to hoover up anything that strays too close. A chameleon is also a deadly shot, and fast. It has to be. Its prey's reflexes are just as fast, with a spring-loaded jump to catapult out of danger. But the chameleon's tongue is faster. Too fast for it to use muscle power alone. High-speed analysis shows that the base of the tongue is wrapped in elastic fibers that are slowly stretched by muscles. The chameleon then releases the fibers, firing its tongue out of its mouth in the same way an archer releases an arrow. But the chameleon's tongue isn't the fastest. Some toads are even faster. Now you see it, now you don't. Slowing this down 100 times shows that the toad has an additional trick. As well as being spring-loaded, its tongue is hinged at the front of its mouth and flicks out to snatch a passing meal. In the laboratory, the Colorado river toad seemed to have the fastest tongue ever measured, a world record holder, until recently. Now its place has been taken by a salamander. the most explosive tongue on the planet, hitting its target in just 7/1000ths of a second. High-speed photography has taught us a lot about the natural world. But scientists were using photography to freeze time as soon as photography was invented. One of these pioneers was Edward Muybridge in 1877. He wanted to know whether a trotting or galloping horse was ever completely airborne, something impossible to see in normal time. To find out, Muybridge set up a series of 24 cameras. Each triggered a fraction of a second after its neighbor had fired. And he showed that when trotting and galloping, all four of a horse's feet do leave the ground together. Muybridge just viewed his pictures as stills, but a sequence of stills makes a movie. Just a few years after Muybridge's experiment, such movies were all the rage, inspired by, of all things, a sneeze. In the 1890s, Thomas Edison filmed a man called Fred Ott in the act of sneezing that could be shown on one of Edison's many inventions, the kinetoscope. In this device, the images were shown one after the other fast enough to fuse them into a single moving image. Devices that blur still images into movies had been around for some time. For example, the zoetrope was invented in the 1830s. These inventions work because we don't see the individual images beyond a certain frequency. But Edison could never fool a fly like this. Inspired by Fred Ott's sneeze, the first ever copyrighted movie, the movie industry really took off at the end of the 19th century when Edison filmed the last images of the Wild West. The Ghost Dance of the Sioux. And the first movie, Kiss, caused quite a stir when it was shown. Camera designs improved quickly, and better ways of projecting films meant they could be enjoyed by large audiences at the same time. And newer cameras could film at faster speeds, slowing down the world for our entertainment and education. In the digital age, cameras don't need film. This camera records images at 10,000 frames a second directly onto a computer, and so slows down time by a factor of 400. Muybridge would have been delighted and intrigued to see the world like this. Although Muybridge didn't need to view his images as movies, his stills can be made into film loops. Very impressive for his day. He was among the first to realize that slowing down or freezing time could reveal secrets of our everyday world. But now there are cameras that slow down time even further. More than 1 million times. Vital in understanding what happens at extremely high velocities. In 2003, disaster struck NASA's space shuttle program. After an apparently normal mission, the orbiter Columbia re-entered the Earth's atmosphere. Over Nevada, Columbia was glowing as brightly as Venus, as friction heated its outer skin. Then a few minutes later, over Texas, it disintegrated.
Fido, when are you expecting tracking? 1 minute to go, flight.
GNC flight.
Flight GNC.
Shock silenced the usually frenetic Mission Control Center. But what had happened? Rerunning the high-speed cameras that routinely monitored takeoff, NASA scientists saw a tiny piece of insulation foam break off and hit the wing. But how much damage could a piece of soft foam do? NASA scientists set about finding out. They fired blocks of similar foam at bits of the shuttle and filmed the impacts with the latest ultra-high-speed cameras. The results were astounding. At the incredible speeds reached by spacecraft, foam behaves like a cannonball. Even a glancing blow could rip a gaping hole. With this information, NASA scientists could redesign key parts of the shuttle. And 3 years after the loss of Columbia and her crew, another shuttle left the launch pad in Florida to return to space. Each launch is now monitored by many high-speed cameras. The safety of our adventures in space depends on this ability to manipulate time. Because we can slow down time, we can analyze such high-speed events in incredible detail. But these same techniques also reveal how beautiful the world can be beyond our everyday perceptions. But there's one explosion that's too fast for even the fastest of cameras. Hundreds of millions of these firework displays can happen in the single blink of an eye. They're created by firing particles such as protons into each other to break them apart and see what they contain. Some of the fundamental particles released by these explosions live for vanishingly short times, around 1/10 of a billionth of a second. And the harder the original protons are smashed together, the more spectacular the result. This is the Large Hadron Collider at CERN, or it will be when it's finished. A long tunnel is being cut through solid rock deep under the border of France and Switzerland. Inside this, a 27-kilometer-long ring, surrounded by superconducting magnets, will smash protons together with more force than ever before. Some scientists think that the protons will hit with enough energy to create wormholes, tears in space-time that might allow particles to travel forward or backwards in time, shattering the ultimate limits of our time perception. It'll take a proton just 1/10,000th of a second to travel round this whole ring, in the process crossing between France and Switzerland several times. When they collide, they'll have reached 99.9999% of the speed of light. And the speed of light is the ultimate speed limit in the universe. Nothing can go faster than that. Or can it? At these small scales, the universe is a very weird place. It's possible for a particle to hit a barrier and appear instantaneously on the other side, something known as quantum tunneling. Scientists have now sent microwaves through a 12-centimeter thick barrier at faster than light speeds, and their signal carried information. It was encoded with a part of Mozart's 40th Symphony. These events happen so fast that if we slow down time enough to witness them, our lives would last billions of years. Much of our world is hidden from us because it happens too fast. In the single blink of an eye, a fly beats its wings 20 times. A salamander can catch its dinner. And millions of elementary particle firework displays could happen. But events that happen too slowly for us to see can also be revealed by modern technology. Watching what happens when we speed up time more and more is the second part of our journey. The world of plants changes much more slowly than ours, so we need to accelerate time to see how they live. Like us, plants also perceive time. They measure the changing length of days throughout the year, which tells them when to flower. And some plants only flower at certain times of the day. Each flower of a morning glory opens in the morning and fades by the afternoon. The plant world looks serene in comparison to our own when viewed at this speed. Viewed like this, cities change and grow before our eyes. On the scale of days, months, and years, new patterns emerge in the natural world. The Earth spins on its axis, creating day and night. As it spins, the sun and moon appear to rise and set when viewed from the Earth. Even in the modern technological world, our lives are still intertwined with these natural patterns. The spinning of the Earth does more than just create day and night. The Earth, Sun and Moon are locked in their swirling dance by gravity. The gravity of both Sun and Moon exert a pull on our planet. But only water is free to respond to this force. So, as the Earth turns beneath them, the gravitational pull of Sun and Moon causes tides to rise and fall. The shape of the ocean basins influences the timing and heights of the tide. One of the biggest tides of all occurs here, around the southwest coast of England, where the water can rise more than 10 meters. The dance of Earth, Moon and Sun is a complex one. Roughly every 28 days, the Moon makes an orbit of the Earth. So each night, it rises in a different place, and a different amount is lit by the Sun. Over this lunar month, the Moon goes from full, through new, and back to full again. And this changing relationship of the Sun and the Moon also affects the height of the tide. When the Sun and Moon line up, when the Moon is either new or full, the tides are higher, spring tides. And when Sun and Moon are at right angles to each other, when the Moon appears half-lit, the tides are smaller, neap tides. Some creatures can track these changes. Horseshoe crabs have followed the Moon's cycles for several 100 million years. They lay their eggs on the beach out of reach of predatory fish, but only crawl out of the water to spawn around the spring tides. This means their eggs will be safely buried in the sand until the next spring tide washes them out. These monthly cycles of the Moon are also important to us. We may have spent a lot of time working out how to measure seconds, minutes, and hours accurately, but we've also taxed our brains over how to measure months and years. Because of the complex relationship between Sun, Moon, and Earth, developing calendars has been, and still is, fraught with problems. Some calendars are based on the Moon's cycle. For example, the Islamic year is 12 lunar months, each month starting with the rising of the crescent moon. This is the calendar used to determine religious festivals and events. Other calendars, such as the Gregorian calendar used by the Western world since 1582, are based on our yearly journey around the sun. Such solar calendars are better synchronized with the yearly pulse of the planet, the cycle of the seasons. The Earth is tilted on its axis, so as it orbits the sun, sometimes the northern hemisphere faces towards the sun, creating summer, and at other times it faces away, creating winter. Calendars that predict the seasons have been vital for millennia. They tell us when to plant our crops. But lunar and solar calendars don't sync up. The Islamic calendar drifts by 11 days a year against the Gregorian one. Yet the Hebrew calendar combines both solar and lunar cycles, though it does need to add a month every now and then to make it work. The sun and moon do sync up over longer periods, but to see this happen, you'll have to wait a little over 19 years. Over this period, the position of the full moon at a particular time of night changes in relation to the background of fixed stars. But every 19 years, it returns to the same position. This is the metonic cycle of the moon. And because the Hebrew calendar combines lunar and solar cycles, it too repeats over the metonic cycle. The metonic cycle also features in the complex calculations that decide when Easter Sunday falls, since Easter relates to the cycle of the moon and of the sun, being the first Sunday after the first full moon after the spring equinox. Viewed from this time perspective, the world changes in surprising ways. Cycles of wetting and drying will cover this statue in a beautiful green patina, formed as crystals grow and flower like a miniature garden. But we're now watching time pass faster and faster. These crystals take about 20 years to grow like this. As our perceptions of time extend to even longer periods, it's not just miniature landscapes that change before our eyes. On the scale of tens of thousands of years, the nature of the planet changes completely. And that's because the Earth wobbles on its axis, giving us a dizzy ride around the sun. The shape of the Earth's orbit also varies, over a period of 100,000 years. At the same time, the direction of the Earth's axis changes over a period of 23,000 years, like a slow-motion spinning top running down. If we speed up this wobble, the angle of the Earth's axis also changes every 41,000 years. The combination of all these cycles means that there are times when the northern hemisphere receives less heat from the sun, triggering the polar ice cap to grow. When the wobbles combine to heat the pole again, the ice cap melts. This long-term cycle, called the Milankovitch cycle, has shaped our history for hundreds of thousands of years, as ice ages have come and gone. With each advance of the ice sheets, habitats change. Woodlands give way to scrub, then tundra. When our perceptions extend to take in millions of years, it's not just habitats that change. The continents are in constant motion over the surface of the planet, drifting at about the same rate that fingernails grow. The Pacific is shrinking as, around the margins, oceanic crust is disappearing beneath the continents, which creates volcanoes. Viewing time at this speed, the whole Pacific Rim lights up with volcanic eruptions. Now it's clear why this is called the Ring of Fire. And what of the longest views of time? Nothing stays constant. Our whole universe is now involved in the dance. Using powerful supercomputers, we can predict the steps in this dance. Our galaxy, the Milky Way, will collide with our nearest neighbor, Andromeda. So much of a galaxy is space, it's unlikely that individual stars will collide, but over billions of years, gravity will drag stars into new patterns and eventually into a new, combined galaxy that scientists have called Milky-Media. This is an accurate simulation of what is likely to happen, though this beautiful display will take billions of years to unfold. Is there a limit to how far we can extend our perceptions of time? Some scientists think the universe will go on expanding. Matter and energy will become stretched so thin that anything that happens will be on unimaginable timescales of trillions of years. And it's possible that this slow, low-energy universe will just spontaneously tunnel into a lower energy state in the quantum vacuum. Disappear. Perhaps a new universe with different laws of time and space will emerge. A new Big Bang with a different story to tell. But that's a place beyond human comprehension. In the 1790s, William Blake wrote, "If the doors of perception were cleansed, everything would appear to man as it is, infinite." Since Blake wrote those words, technology has opened the doors of perception to show us our world in new and magical ways.